Right now, as you hear these words, something is happening inside your skull that no scientist on Earth can fully explain, and it may involve the same force that bends light around a black hole. There is roughly 3 pounds of soft, pinkish, tofu-textured tissue sitting inside your head. Nowhere on that tissue is your name written. Nowhere on it will you find your face, your memories, or the dream you had last night. What you will find is cells, water, and electricity. And yet, right now, you are undeniably feeling something. The glow of this screen, the rhythm of these sentences, and that persistent, unshakable sense of I, the one doing the reading, the one doing the feeling. The phenomenon we are talking about is the single most familiar thing in the universe and, simultaneously, the single most inexplicable. We call it consciousness. Science, over the past few centuries, has decoded the birth of stars, proved that time itself stretches and contracts, mapped the genomes of thousands of species, and sent robots to the surface of Mars. But one puzzle remains stubbornly, almost embarrassingly, unsolved. Why does a lump of matter, mere biological tissue obeying the laws of chemistry and physics, generate subjective experience? Why is there something it is like to be you? The philosopher David Chalmers, then at Washington University and now at New York University, gave this puzzle its modern name in 1995. He called it the hard problem of consciousness with a capital H, to distinguish it from what he considered the comparatively easy problems, explaining how the brain processes sensory input, integrates information, controls behavior, and focuses attention. Those tasks are monstrously difficult in practice, of course, but they are at least the kind of problems that we know how to approach. We build models, run experiments, write equations, and eventually we crack them. The hard problem is of a fundamentally different nature. It is asking not how the brain does what it does, but why all of that doing is accompanied by experience at all. Neuroscientists can already identify which neurons fire when you see the color red. They can trace the electrical signal from your retina through the lateral geniculate nucleus and into the primary visual cortex. They can measure the precise wavelength of light that triggered the cascade. What they cannot do, what nobody can do, is explain why that cascade of electrochemical events produces the vivid, subjective, first-person sensation of redness. That inner glow, that felt quality, is what philosophers call qualia. The redness of red, the sharp sting of pain, the warmth of a sip of fresh coffee on a cold morning, these are qualia. They are, in a sense, the most obvious things in existence. Every waking moment of your life is saturated with them. Yet they are also profoundly mysterious, because no matter how precisely you describe the physics or the chemistry, you cannot hand your qualia to another person. You cannot even confirm that the red you see is the same red someone else sees. There is, at present, no instrument that can measure the interior of an experience. And so we arrive at a strange impasse. The most advanced civilization in the known history of the cosmos has figured out how to split atoms, edit genes, and detect gravitational waves from colliding neutron stars a billion light-years away. But it cannot explain why looking at a sunset feels like anything at all. That impasse is where this story begins. But rather than wandering into philosophical abstraction, we're going to follow a very specific trail of evidence and argument, one that leads, improbably, from the elegant mathematics of black holes to the warm, wet interior of the human brain. At the heart of this trail is a hypothesis so audacious that it was mocked for decades and so strange that even now it divides the scientific world. The hypothesis states that consciousness is not merely the hum of electrical signals bouncing between neurons. Instead, it is something that arises from deep within the cell, at a scale so small that the ordinary rules of physics no longer apply, a scale where the fabric of spacetime itself buckles, bends, and collapses. The person who proposed this idea is not a mystic or a self-help guru. He is one of the greatest mathematical physicists of the modern era, a man who proved with pure mathematics that black holes must contain a singularity, a point where matter is crushed to infinite density, and the known laws of physics break down entirely. For that proof, he received the Nobel Prize in Physics in 2020. His name is Roger Penrose, and he was born in Colchester, England, in 1931. The same year Kurt Gödel shook the foundations of mathematics. That coincidence is more than poetic. because it was Gödel's work that set the stage for everything Penrose would later claim about the human mind. To understand why a physicist who spent his career studying the geometry of the cosmos turned his attention to the mystery of consciousness, and to evaluate whether his extraordinary claim has any chance of being right, we need to begin with the conventional picture of the brain, the picture that works beautifully right up until the moment it does not. Open any modern neuroscience textbook, and you will find the brain described in terms that would not sound entirely out of place in a conversation about computer hardware. The human brain contains approximately 86 billion nerve cells, known as neurons, a number established by the Brazilian neuroscientist Susana Herculano Hausel and her team, who in 2009 published a landmark paper using a method called isotropic fractionation to arrive at this figure, which displaced the older and rounder estimate of 100 billion that had circulated for decades. Each of those 86 billion neurons is connected to other neurons at junctions called synapses. A single neuron may have anywhere from 1,000 to 10,000 synaptic connections, and the total number of synapses in the adult brain is estimated at roughly 100 trillion, a figure so large that it dwarfs the number of stars in the Milky Way galaxy, which NASA estimates at somewhere between 100 billion and 400 billion. In other words, there are more connection points inside your skull than there are suns in the entire galaxy overhead. Neurons communicate using a combination of electricity and chemistry. When a neuron is sufficiently stimulated, it fires, that is, an electrical impulse called an action potential races down its long, thin extension, the axon, at speeds that can reach roughly 270 miles per hour in the fastest fibers. When that impulse arrives at a synapse, it triggers the release of chemical messengers called neurotransmitters, molecules such as glutamate, dopamine, serotonin, and GABA. These molecules drift across the tiny synaptic gap and bind to receptors on the neighboring neuron, either encouraging it to fire in turn or suppressing it from doing so. This relay of electrical spikes and chemical handshakes is happening everywhere in the brain simultaneously, billions of times per second, in staggeringly intricate patterns. It is a system of almost inconceivable complexity, and the metaphor that scientists have found most useful for describing it is the computer. Just as a computer is built from billions of transistors, tiny switches that are either on or off, representing the binary digits 0 and 1, the brain appears to be built from billions of neurons that are either firing or not firing. Wire enough transistors together in the right configuration, and you get a machine that can play chess, recognize faces, or generate human-sounding language. Wire enough neurons together, and you get a system that can do all of those things and vastly more. This analogy has been spectacularly productive. It inspired the entire field of artificial intelligence, beginning with the McCulloch-Pitts model of the neuron in 1943 and running through the perceptrons of the 1950s, the backpropagation revolution of the 1980s, and the deep learning explosion that now powers everything from self-driving cars to the language model you may be interacting with right now. Every time an AI achieves a new benchmark, beating a human grandmaster at chess, passing a bar exam, generating a photorealistic image from a text prompt, it is, in some indirect sense, a testament to the power of the brain as computer metaphor. But here is the problem. The metaphor works perfectly for explaining what the brain does, and yet says nothing at all about what it is like to be a brain. And there are at least two specific places where the computational picture of the brain cracks open, revealing chasms that no amount of additional wiring can bridge. The first crack is called the binding problem. Consider a simple scene. A red apple rolls across a wooden table. When you see this, your brain does not process it as a single, unified event. Different attributes of the scene are handled by different neural populations in different regions of the cortex, often at slightly different times. The color red is processed in an area called V4. The shape, the roundness of the apple, is handled by neurons in the inferotemporal cortex. The motion, the rolling, is tracked by area V5, also known as MT. There is even a slight temporal lag. Studies have shown that the brain registers color a few milliseconds before it registers motion. And yet, when you look at the scene, you do not experience a disjointed collection of fragments, redness over here, Roundness over there, motion arriving a beat late. You see a single, seamless event, a red, round apple rolling across a table, all at once. All bound together into one unified picture. Who or what is doing the binding? Where in the brain is there a screen on which all the separately processed features are reassembled into a single, coherent experience? The answer, as far as anyone can tell, is nowhere. There is no master theater in the brain, no central screen. No little person, no homunculus, sitting in a control room watching the show. The binding happens, but no one can point to the place where it happens or explain the mechanism by which it happens. This is the binding problem, and it has resisted decades of investigation. The second crack is deeper still, and it is, of course, the hard problem itself. Suppose that science advances to the point where we can record every single neuron firing in a person's brain at the exact moment they see a red apple. Suppose we can map every synapse, trace every signal, and build a complete computational model that perfectly predicts the person's behavior, when they will reach for the apple, what words they will use to describe it, how their pupils will dilate. We would have achieved something truly extraordinary. And yet we would still have explained only the function, the mechanism, the information processing. We would have explained the easy problems. The question of why all of that processing is accompanied by the felt experience of redness, why there is something it is like to see the apple, would remain exactly as mysterious as before. The philosopher Daniel Dennett spent much of his career arguing that this question is itself confused. That once you have explained all the functions, there is nothing left over to explain. But many other philosophers and a growing number of neuroscientists disagree. They point to a famous thought experiment, the philosophical zombie. A philosophical zombie, sometimes abbreviated P-zombie, is a hypothetical being that is physically identical to you in every respect. It has the same brain, the same neurons, the same synaptic connections, the same electrochemical activity. It walks, talks, laughs, cries, and reports that it sees the color red. And yet, on the inside, there is nothing. No experience. No qualia. No felt sense of anything. The lights are on, but nobody is home. The question is, if the brain is truly just a complex electrical circuit, then what prevents us from being philosophical zombies? What is the extra ingredient that makes us conscious rather than merely computational? If you cannot point to a specific physical mechanism and say, this is why the lights are on, then you have not solved the problem. You have merely described the wiring. Here, at the boundary of neuroscience and philosophy, the conventional picture of the brain falls silent. The transistor metaphor, for all its power, has nothing to say about why flipping switches should feel like anything. The answer, if there is one, must lie somewhere else, somewhere deeper, somewhere stranger, somewhere the textbooks have not yet reached. One person felt this in his bones. He was not a brain scientist. He had spent his life not inside skulls but inside equations, tracing the geometry of the universe at its most extreme. And what he found there would lead him to the most controversial claim of his career, that the answer to consciousness lay not in the connections between neurons, but in the architecture of spacetime itself. Roger Penrose came to the consciousness question from a direction that no neuroscientist would have predicted. His background was in mathematical physics, and his reputation rested on work of almost breathtaking abstraction. In the 1960s, working alongside Stephen Hawking, then a young graduate student at Cambridge, Penrose developed a series of theorems about the structure of space-time under extreme gravitational conditions. The most famous of these, published in 1965 in the journal Physical Review Letters, proved that if general relativity is correct, then under certain very general conditions, gravitational collapse must produce a singularity, a point of infinite density where the known laws of physics cease to function. This was not a speculation or an approximation. It was a mathematical proof, as rigorous as anything in pure mathematics. And it meant that black holes were not merely a theoretical curiosity, but an inevitable consequence of Einstein's equations. For this work, Penrose shared the 2020 Nobel Prize in Physics with Reinhard Genzel and Andrea Ghez, who provided observational evidence for the supermassive black hole at the center of our own galaxy. But long before the Nobel Committee came calling, Penrose had already turned his attention to a question that seemed, on the surface, to have nothing to do with black holes or singularities. In 1989, he published a book called The Emperor's New Mind, and in it he made a claim that stunned the scientific world. The human mind, he argued, is not a computer. Not because it is merely a very complicated computer, or a computer made of unusual hardware, but because the mind does something that no computer, no matter how powerful, can ever do. The claim rested on a piece of mathematics from 1931, the work of Kurt Gödel, the Austrian logician who had emigrated to the United States and spent his final decades at the Institute for Advanced Study in Princeton, New Jersey, walking the same paths as Albert Einstein. Gödel's incompleteness theorems are among the most profound results in the history of mathematics, and they are worth understanding in some detail, because everything Penrose says about consciousness ultimately flows from them. Mathematics, at its foundations, is built on formal systems. A formal system is a collection of axioms, basic assumptions accepted without proof, and rules of inference that allow you to derive new truths from those axioms. Euclidean geometry, for instance, is a formal system. You start with a handful of postulates about points, lines, and planes, and you derive an entire universe of geometric truths. The dream of early 20th century mathematicians, most notably David Hilbert, was to put all of mathematics on a single, secure, formal foundation, to find a set of axioms and rules from which every true mathematical statement could, in principle, be derived. This was Hilbert's program, and it was the mathematical equivalent of a quest for the Holy Grail. Gödel destroyed it in a single paper. His first incompleteness theorem, published in 1931, proved that for any consistent formal system powerful enough to express basic arithmetic, addition, multiplication, the natural numbers, there will always exist true statements within the scope of that system that the system itself cannot prove. Not because the system is poorly designed, or because we have not been clever enough, but as a matter of logical necessity. The system is inherently, inescapably incomplete. There will always be truths that lie beyond its reach. Now, here is where Penrose enters the picture. A computer, at its core, is a formal system. It operates by following an algorithm, a fixed set of rules, a step-by-step procedure. Alan Turing formalized this idea in 1936 with his concept of the Turing machine. And every digital computer ever built, from the room-sized ENIAC of 1945 to the latest server farm processing trillions of calculations per second, is a physical instantiation of a Turing machine. If a computer is a formal system, then Gödel's theorem applies to it. This means that for any given computer, there will be mathematical truths that it cannot prove, statements that are, relative to its programming, forever out of reach. But Penrose observed something remarkable. Human mathematicians can see these truths. We can step outside the formal system, look at a Gödel sentence, a statement that says, essentially, I am not provable within this system, and recognize that it is true. Not by following an algorithm, not by grinding through a mechanical proof, but by a flash of insight, a direct apprehension of mathematical reality. If the human mind were merely a computer, Penrose argued, it too would be trapped within a formal system. It too would be unable to see the truths that Gödel proved to be unprovable. But it can see them. Therefore, the mind is not a computer. It does something that is, in a precise technical sense, non-computable. This argument, known as the Penrose-Lucas argument, because the philosopher John Lucas had advanced a similar idea in 1961, is fiercely debated. Critics have attacked it from multiple angles. The mathematician Solomon Fieferman argued that human mathematical understanding is itself inconsistent and therefore not subject to Gödel's theorem in the way Penrose assumed. The AI pioneer Marvin Minsky pointed out that humans can believe false statements to be true, which means our reasoning is not the kind of perfectly consistent system that Gödel's theorem addresses. The philosopher Hilary Putnam and others have raised similar objections. And the consensus among logicians and philosophers of mathematics is that the Penrose-Lucas argument, at the very least, does not constitute a rigorous proof. But Penrose was undeterred. Whether or not the argument is airtight, he was convinced of the central insight that human understanding involves something non-computable, something that transcends any algorithm. And once he had that conviction, a new question immediately presented itself. If the mind is non-computable, then what is the physical basis of that non-computability? It cannot reside in the classical laws of physics, because those laws are, at least in principle, perfectly computable. Given the initial conditions of a classical system and the laws governing its evolution, you can theoretically compute the entire future of the system to arbitrary precision. Newtonian mechanics is computable. Maxwell's electrodynamics is computable. Even general relativity, despite its fearsome mathematical complexity, is computable in this sense. So if there is a non-computable process in nature, it must come from somewhere else. Penrose searched the known landscape of physics and found exactly one candidate: quantum mechanics. Specifically, he found it in the single most mysterious and contentious aspect of quantum mechanics, the process by which a quantum superposition collapses into a single definite outcome. This is where the story takes its sharpest and most unexpected turn, plunging us from the world of abstract mathematics into the weird, counterintuitive heart of quantum physics. In everyday life, objects have definite properties. A baseball is either in your left hand or your right hand, not both simultaneously. A coin once flipped is either heads or tails. But in the quantum world, the world of electrons, photons, and atoms, this certainty dissolves. A particle can exist in a superposition of states, meaning it is, in a very real sense, in multiple states at the same time. An electron, for instance, can be in a superposition of spinning clockwise and spinning counterclockwise simultaneously. A photon can be in a superposition of traveling along path A and path B at the same time. This is not a metaphor. It is not a statement about our ignorance. Quantum mechanics, as a mathematical framework, explicitly describes particles as existing in these blended, overlapping states. The mathematical object that encodes all of this information is called the wave function. The wave function is like a shimmering cloud of possibility. It tells you, at any given moment, the probability of finding the particle in each of its possible states. If you have not yet looked at the electron, if you have not measured it, the wave function says it is both clockwise and counterclockwise, with various probabilities. But the moment you do look, the moment you perform a measurement, something dramatic happens. The wave function collapses. The shimmering cloud of possibilities snaps into a single definite outcome. The electron is clockwise, or counterclockwise, never both. This transition from many to one, from possibility to actuality, is called wave function collapse. And it is, without exaggeration, the deepest unsolved problem in all of physics. The standard textbook treatment, known as the Copenhagen interpretation, essentially says, the collapse happens when someone observes the system. But this raises profound questions. What counts as an observation? Does a conscious observer have to be present? Can a camera count? A thermostat? A rock? Physicists have fought over these questions for nearly a century, and there is still no consensus. Penrose found the standard answer deeply unsatisfying. He did not believe that the universe sits around in a fog of superposition waiting for a human being to take a look. He wanted a physical mechanism, a concrete process in the natural world that causes the collapse, independent of any observer. And he found one, hiding in the most unexpected place, gravity. Here is the argument, and it is one of the most elegant pieces of reasoning in modern physics. General relativity, Einstein's theory of gravity, tells us that mass curves spacetime. The sun curves the spacetime around it, creating the gravitational well in which the Earth orbits. A neutron star curves spacetime far more dramatically. A black hole curves it so extremely that nothing, not even light, can escape. Now imagine a quantum superposition of a tiny particle, say a small dust grain, being in two places at once. Location A and location B. That grain, however tiny, has mass. And mass curves spacetime. So if the grain is in superposition, simultaneously at A and at B, then spacetime itself must be in superposition, simultaneously curved one way, as if the grain were at A, and curved another way, as if the grain were at B. Two different geometries of spacetime, stacked on top of each other. Penrose argued that this is fundamentally unstable. Spacetime, he proposed, cannot sustain two contradictory geometries for very long. It is like a fabric being pulled in two different directions at once. Eventually, the tension must resolve, and the fabric must settle into one shape or the other. This self-resolution, this spontaneous collapse of the superposition driven by the gravitational instability of two overlapping spacetime geometries, is what Penrose called objective reduction, or OR. The word objective is crucial. It means the collapse is a real, physical event that happens whether or not anyone is watching. It is not triggered by observation. It is triggered by gravity. Penrose even derived a beautifully simple formula that predicts how long a given superposition can persist before gravity forces it to collapse. The formula is tau is almost equal to /E_g, where tau is the time until collapse. H bar is the reduced Planck constant, a fundamental constant of nature with a value of approximately 1.055 times 10 superscript 3 joule seconds. Setting the scale of quantum phenomena, and E_g is the gravitational self-energy of the superposition, essentially a measure of how much the two superposed spacetime geometries differ from each other. The formula tells us something wonderfully intuitive. If the superposed object is heavy, say a basketball, then E_g is enormous, because the two spacetime geometries are very different from each other. A large E_g means a tiny tau, which means the superposition collapses almost instantaneously. That is why we never see basketballs in two places at once. They collapse into one definite location so fast that no instrument could ever catch them being in. 2. On the other hand, if the object is extremely light, a single electron, say, then E_g is vanishingly small, and tau becomes astronomically large. The superposition could persist for millions of years. That is why electrons can remain in quantum superposition indefinitely, doing all the strange quantum things that electrons do, tunneling through barriers, interfering with themselves, entangling with distant partners. The key insight is this: somewhere between the scale of an electron and the scale of a basketball, there is a crossover zone, a mesoscopic realm, where the superposition lasts just long enough to matter, but eventually collapses in a time frame that is relevant to biological processes. Penrose calculated that for a system of about 1 billion tubulin molecules, a number that could plausibly be assembled in a neuron, the gravitational self-energy would yield a collapse time of roughly 25 milliseconds. And now comes the most audacious step in the entire chain of reasoning. Penrose proposed that these moments of gravitational collapse are not merely physical events. Each one, he suggested, is a moment of proto-consciousness, a tiny flicker of experience, a quantum of awareness, the non-computable choice that occurs when spacetime resolves its own contradiction is, Penrose hypothesized, the very thing that makes human understanding possible. It is the physical basis of the non-computability that he had identified through Gödel's theorem. It is the source of qualia. It is where the redness of red comes from. If this is right, then consciousness is not something the brain computes. It is something the universe does, a built-in feature of the way spacetime settles its own quantum indeterminacy. And the brain is not a computer that generates consciousness as a byproduct of its processing. It is an exquisitely refined organ that harnesses a fundamental feature of physics, the gravitational self-collapse of superposition, and amplifies it, orchestrates it, and weaves it into the continuous stream of experience that you call your life. But there was a problem. Penrose had the physics, the mathematics, and the philosophy. What he did not have was the biology. Where inside the brain could this process actually take place? He needed a physical structure, something inside neurons that could sustain quantum superposition, long enough for gravitational collapse to occur on a biologically relevant timescale. Penrose knew mathematics. He knew general relativity. He knew quantum theory. What he did not know was the inside of a cell. The answer came from an unexpected quarter. Stuart Hameroff was an anesthesiologist at the University of Arizona in Tucson. His medical specialty gave him an unusual perspective on consciousness, because anesthesiologists are, in a sense, professional consciousness removers. Every day, they administer drugs that cause consciousness to vanish, and then they watch it come back. Hameroff was struck by a curious fact. When a patient goes under general anesthesia, their consciousness disappears completely. And yet most of the brain's electrical activity continues more or less normally. Neural signals still propagate. Synapses still fire. Much of the brain's information processing keeps humming along. What, then, is the anesthetic actually switching off? If consciousness were simply the sum total of the brain's electrical activity, you would expect anesthesia to shut down the electricity. But it does not. It shuts down consciousness while leaving much of the electricity intact. This suggested to Hameroff that consciousness might be rooted not in the electrical signals that pass between neurons, but in something happening inside the neurons themselves, something that anesthetics specifically target. That something Hameroff believed was microtubules. Microtubules are tiny hollow cylinders that form part of the cytoskeleton, the internal scaffolding, that gives every cell its shape and structure. They are found in virtually every cell in the body, but neurons are particularly rich in them. A single neuron may contain millions of microtubule segments, and the brain as a whole contains a number so vast it defies easy comprehension. Each microtubule has an outer diameter of about 25 nanometers, a nanometer being 1/1,000,000th of a meter, or roughly 1/40,000th the width of a human hair. The tube is composed of a protein called tubulin, and the tubulin molecules are arranged in a beautiful, spiraling lattice, like bricks in a helical wall. Each tubulin is a dimer, a pair of protein subunits, alpha-tubulin and beta-tubulin, joined together, and thousands of these dimers stack up to form a single microtubule. Now here is what caught Hameroff's attention. Each tubulin dimer can flex between slightly different conformational states. It has internal degrees of freedom. And in the mid-1980s and early 1990s, Hameroff began to speculate that these tubulin states might function as the bits of a biological computer, not a classical computer, but a quantum computer. A classical bit can be either 0 or 1. A quantum bit, a qubit, can be 0, 1, or a superposition of both simultaneously. If each tubulin could exist in a quantum superposition of two conformational states, then an array of tubulins in a microtubule would constitute a quantum register, a line of qubits capable of performing quantum computation. And if millions of microtubules across thousands of neurons could entangle their quantum states, the brain would contain a quantum computer of staggering power, operating not at the scale of synapses and electrical signals, but at the far smaller, far more fundamental scale of molecular physics. Hameroff read Penrose's The Emperor's New Mind and recognized a perfect fit. Penrose needed a biological substrate for his gravitational collapse process. Hameroff had a candidate, microtubules. The two men met, corresponded, and by the mid-1990s had forged their ideas into a single, unified theory. They called it Orchestrated Objective Reduction, Orchestra or for short. The objective reduction part is Penrose's contribution. The gravitational collapse of quantum superposition. The orchestrated part is Hameroff's. The idea that this collapse does not happen randomly in isolated particles, but is orchestrated, coordinated, organized, conducted like an orchestra by the biological structure of the microtubule network within neurons. In the Orchestra OR model, here is what happens. Tubulin proteins within microtubules enter quantum superpositions. These superpositions do not occur in isolation. They spread and entangle across many tubulins within a microtubule, across many microtubules within a neuron, and possibly across many neurons connected by gap junctions, tiny channels that directly link the interiors of adjacent cells, allowing ions and small molecules to pass between them. As the superposition grows, as more and more tubulins become entangled and the total mass involved in the superposition increases, the gravitational self-energy E_G in Penrose's formula rises. When E_G reaches a critical threshold, the superposition becomes gravitationally unstable, and it collapses. All at once, in a single coordinated event. One moment, the tubulin network is in a shimmering quantum superposition of many possible states. The next moment, it has snapped into a single definite configuration. This snap, this orchestrated moment of objective reduction, is, according to the theory, a single moment of conscious experience. And how often does it happen? Penrose and Hameroff calculated the numbers and arrived at a figure that sent a chill through everyone who heard it. Approximately 40 times per second. 1 moment of consciousness every 25 milliseconds. 40 conscious moments per second. That number, 40 Hz, is not arbitrary. It is, in fact, one of the most studied rhythms in all of neuroscience. Gamma oscillations, brain waves in the 30 to 90 Hz range with a peak around 40 Hz, have been associated with conscious awareness, attention, sensory binding, and working memory for decades. In the early 1990s, the neuroscientists Wolf Singer and Charles Gray at the Max Planck Institute demonstrated that neurons representing different features of a visual scene synchronize their firing at roughly 40 Hz. And many researchers since then have proposed that this gamma synchrony is the neural correlate of conscious binding, the mechanism that stitches separately processed features into a unified experience. The fact that the orchestra or theory independently predicted a 40 Hz rhythm for consciousness, derived not from any neuroscience data but from the physics of gravitational collapse, was an astonishing coincidence, if it was a coincidence. Think of it this way. Your conscious life, according to Orchestra OR, is like a film. Each frame of the film is a single quantum gravitational collapse event, a flash of spacetime, settling into a definite shape. These frames are projected at a rate of 40 per second, and they blend together into the seamless, flowing stream of subjective experience that you know as being alive. And this model also offers an answer to the binding problem. The reason your experience is unified, the reason you do not perceive the redness of the apple and its roundness and its rolling as separate, disconnected events, is that the quantum collapse is a single, all-at-once event. When the superposition collapses, it collapses everywhere it has spread at the same instant, binding all the entangled information into a single coherent outcome. The binding happens not at the level of neural circuits, but at the level of spacetime itself. But if this sounds too beautiful, too elegant, too perfectly tailored to the problem, it is because it is. And in the year 2000, a physicist arrived with a knife. Max Tegmark, a Swedish-born cosmologist then at the University of Pennsylvania and now at MIT, published a paper in the journal Physical Review that many scientists considered a death blow to the orchestra or theory. His argument was devastatingly simple. The brain, he pointed out, is warm, wet, and noisy, quite possibly the worst environment imaginable for sustaining quantum coherence. Quantum coherence, the delicate property that allows particles to remain in superposition and entangle with each other, is extraordinarily fragile. Any interaction with the environment, a stray thermal vibration, a collision with a water molecule, an encounter with an electromagnetic field, can destroy it. This process of destruction is called decoherence. Decoherence is, in a sense, the enemy of quantum mechanics. It is the reason we do not see quantum effects in everyday life. It is the reason a baseball does not tunnel through a wall, even though quantum mechanics says there is a minuscule probability that it could. And it is the reason that the engineers who build real quantum computers go to extraordinary lengths to protect their systems from environmental interference. The quantum processors made by companies like Google and IBM are cooled to temperatures near absolute zero, roughly negative 460 degrees Fahrenheit, and operated in ultra-high vacuum, isolated from every conceivable source of disturbance. Even so, decoherence remains the single greatest engineering challenge in quantum computing. And the qubits in these machines can only maintain their quantum states for microseconds to milliseconds before the environment intrudes and the coherence is lost. Now consider the human brain. Its operating temperature is approximately 98.6 degrees Fahrenheit, roughly 310 Kelvin, which is about 300 degrees warmer than the operating temperature of a commercial quantum computer. It is saturated with water. Molecules are in constant, violent thermal motion. Chemical reactions are occurring at a furious rate. Electromagnetic fields are everywhere. If there is a setting more hostile to quantum coherence than the interior of a living brain, it would be difficult to imagine one. Tegmark calculated the decoherence time for a quantum superposition in a microtubule at brain temperature. His result was crushing, approximately 10 superscript 1 superscript 3 seconds, 1/10 trillionth of a second, a timescale known as a femtosecond. That is how long a quantum superposition in a microtubule would last before the warm, wet, noisy environment of the brain destroyed it. But Orchestra OR requires the superposition to persist for approximately 25 milliseconds, the time needed for one conscious moment at 40 Hz. The gap between what physics allows and what the theory demands is not a small discrepancy. It is a chasm. Tegmark's femtosecond is roughly 100 billion times shorter than the 25 milliseconds that Orchestra OR needs. To put this in perspective, if the quantum state could last for 1 second, the required duration would be the equivalent of roughly 8,000 years. Asking a microtubule in the brain to maintain quantum coherence for 25 milliseconds, given Tegmark's calculation, is like asking a sand castle to stand for 8 millennia. This was, by any measure, a devastating critique. It struck at the very foundation of the theory. If quantum coherence cannot survive in the brain long enough to do anything useful, then the entire edifice of Orchestra OR, the orchestrated collapses, the gravitational self-energy, the non-computable moments of consciousness, collapses too, and not in the beautiful way Penrose intended. For many scientists, Tegmark's paper was the end of the story. The Orchestra OR theory was filed under noble but impossible, and largely forgotten by mainstream physics and neuroscience. Penrose and Hameroff pushed back. They argued that Tegmark had made errors in his calculations, in particular, that he had assumed a superposition separation distance of tens of nanometers when Orchestra OR actually stipulated femtometer scale separations, which would yield decoherence times 7 orders of magnitude longer. They pointed to the possibility that the ordered water inside the hollow core of a microtubule might provide some shielding from thermal noise. They suggested that the surrounding gel of actin and other proteins might further protect the quantum states. They raised the possibility of biological quantum error correction, a mechanism by which the microtubule lattice itself might resist decoherence in ways that had not been considered. But they could not prove any of this. They had arguments, ideas, and hand-waving. They did not have data. And so, for more than 20 years, the Orchestra OR theory sat in scientific purgatory, a beautiful idea with no experimental support, a theory that explained too much to be ignored and too little to be believed. Then, starting around 2024, the wall began to crack. And the forces doing the cracking were not theoretical arguments, but experimental results, data coming from laboratories around the world, involving real physical measurements on real biological systems. The cracks appeared in 3 main places. The first crack came from a phenomenon called superradiance. In 2024, a research team published a landmark paper in the Journal of Physical Chemistry B, titled Ultraviolet Superradiance from Meganetworks of Tryptophan in Biological Architectures. Tryptophan is an amino acid, one of the 20 building blocks that make up all proteins in the body. It is the same amino acid famously found in turkey, often blamed, incorrectly, for making people sleepy after Thanksgiving dinner. But tryptophan also has an important physical property. It absorbs and emits ultraviolet light. Each tubulin dimer in a microtubule contains 8 tryptophan residues, and these tryptophan molecules are distributed throughout the microtubule lattice at separations of roughly 2 nanometers. When an ordinary collection of molecules emits light, they do so independently, each molecule radiating at its own time, in its own direction, with no coordination. The result is incoherent light, like the glow of a standard light bulb. But superradiance is different. In superradiance, a large number of molecules emit their light in lockstep, all at the same time, all in the same direction, producing a burst of light that is far more intense than the sum of the individual emissions. Superradiance is not a classical phenomenon. It is inherently quantum mechanical. It can only occur when the emitting molecules are in a collective quantum state, when they are, in a sense, behaving as a single coordinated quantum system, rather than as independent individuals. The 2024 study, led by a collaboration of theorists and experimentalists, first predicted theoretically that the tryptophan networks within microtubule-like protein structures should exhibit superradiance, and then confirmed it experimentally. And here is the key detail: the superradiance was observed at room temperature, not at the ultra-cold temperatures of a physics lab. It was observed in warm, complex, protein-based structures, the very kind of environment that Tegmark and others had claimed would destroy quantum coherence in femtoseconds. Even more remarkably, the effect did not weaken as the structures grew larger. It got stronger. Larger tryptophan networks showed more superradiance, not less. This is the opposite of what you would naively expect if decoherence were wiping out all quantum effects as fast as they arise. The experimental team leader, Majid Chergouei, who led the experimental confirmation, said, "It's a beautiful result. It took very precise and careful application of standard protein spectroscopy methods. But guided by the theoretical predictions of our collaborators, we were able to confirm a stunning signature of superradiance in a micron-scale biological system." And Marlon Scully, a physicist renowned for his contributions to quantum optics, commented, "We will certainly be examining closely the implications for quantum effects in living systems for years to come." To be clear, this result does not prove orchestra or superradiance in a tryptophan network is not the same thing as a gravitational collapse of a quantum superposition. But it does something almost as important. It demolishes the assumption that quantum coherence cannot survive in warm biological systems. The wall that Tegmark built, the warm, wet, and noisy argument, developed its first visible crack. The second crack came from anesthesia, the very phenomenon that had first attracted Hameroff's attention decades earlier. In August 2024, a research team led by Professor Mike Wiest at Wellesley College, a liberal arts college in Massachusetts, published a study in the journal eNeuro that produced a result strikingly consistent with the predictions of Orchestra OR. The experimental setup was simple and elegant. The researchers took a group of 8 male Long Evans rats and gave some of them a drug called epothalone B. Epothalone B belongs to a class of drugs originally developed for cancer treatment. It is a microtubule stabilizing agent, meaning it binds to microtubules and makes them more rigid and resistant to disruption. The same class of drugs, called taxanes, is widely used in chemotherapy precisely because cancer cells rely on rapid microtubule dynamics for cell division, and stabilizing the microtubules freezes the process. After administering epothalone B, the researchers exposed the rats to isoflurane, a commonly used anesthetic gas, and measured how long it took them to lose consciousness, operationally defined as the loss of the writing reflex, a standard measure in anesthesia research. The result was unambiguous. Rats that had received epothalone B took, on average, 69 seconds longer to lose consciousness than control rats that had received only a placebo. The effect was large, a Cohen's d of 1.9, indicating a standardized mean difference well above the threshold for what statisticians consider a large effect. The difference was statistically significant, with a p-value of 0.0016. And the researchers carefully controlled for the possibility that the difference was due to the rats simply building up a tolerance to isoflurane over repeated exposures. The tolerance contribution, estimated conservatively, accounted for at most 40 seconds of the 69-second difference, not enough to explain the full effect. Think about what this means. If anesthesia worked solely by acting on ion channels and synaptic receptors, the standard targets, assumed by classical neuroscience, then stabilizing microtubules should have had no effect on how quickly the rats lost consciousness. The fact that it did, that making microtubules more resistant to disruption made consciousness more resistant to being switched off, is exactly what the Orchestra OR theory predicts. Hameroff had argued for decades that anesthetics cause unconsciousness not merely by interfering with synaptic transmission, but by disrupting quantum processes inside microtubules. If that is true, then stabilizing the microtubules should protect those processes and delay the onset of unconsciousness. And that is precisely what happened. This finding was also consistent with earlier clinical observations. A 2015 study had found that human cancer patients who had received taxane chemotherapy, another class of microtubule stabilizing drugs, required more anesthetic during surgery and showed signs of partial resistance to anesthesia. Exactly as you would expect if microtubules play a functional role in the mechanism of consciousness. The Wellesley study provided the first controlled experimental confirmation of this effect in an animal model. The third crack is perhaps the most provocative, and it must be presented with appropriate caution. Recent studies have reported detecting signatures of quantum entanglement in the living human brain. Quantum entanglement is one of the strangest and most rigorously demonstrated phenomena in all of physics. When two particles become entangled, their quantum states become correlated in a way that has no classical analog. Measuring the state of one particle instantaneously determines the state of the other, no matter how far apart they are. Einstein famously derided this as spooky action at a distance, but decades of experiments, culminating in the work that won the 2022 Nobel Prize in Physics for Alain Aspect, John Clauser, and Anton Zeilinger, have confirmed that entanglement is real. A team of researchers used specialized MRI techniques and reported evidence consistent with entangled quantum states in the brain that correlated with heartbeat rhythms and with measures of consciousness and working memory performance. A 2025 paper by Wiest and colleagues, published in the journal Neuroscience of Consciousness, reviewed the accumulating evidence and argued that a quantum microtubule substrate of consciousness is now experimentally supported, not proven, but supported in ways that were unimaginable just a few years ago. The caution here is real and important. None of these experiments directly demonstrates that gravitational collapse of quantum superpositions occurs inside neurons. Penrose's most radical claim, that consciousness arises specifically from objective reduction, driven by gravity, remains unproven. What the experiments do show is that the preconditions for such a process are met. Quantum coherence can survive in warm biological systems. Microtubules are functionally relevant to consciousness, as demonstrated by the anesthesia experiments. And signatures consistent with quantum entanglement can be detected in the brain. The wall has not fallen, but it is cracked and light is coming through. It is also essential to mention the strongest counterarguments that still stand. In addition to the general decoherence objection, a line of criticism published as recently as 2025 points out that endogenous ferritin, an iron storage protein found in all cells, including neurons, interacts with microtubules and quenches their fluorescence and superradiance. The superradiance experiments described above were conducted in purified protein solutions that did not contain ferritin, and critics argue that in the real cellular environment, ferritin would absorb the ultraviolet photons before they could contribute to any quantum process. Furthermore, studies of biophoton emissions from the human body have failed to detect ultraviolet biophotons, suggesting that even if microtubules can exhibit superradiance in the lab, they may not do so inside a living neuron. This is a serious objection, and it has not been fully answered. The philosopher Patricia Churchland once quipped that pixie dust in the synapses is about as explanatorily powerful as quantum coherence in the microtubules, a memorable line that captures the frustration many mainstream scientists feel with quantum consciousness theories. Even David Chalmers, who coined the hard problem, has expressed skepticism that quantum mechanics can resolve it. He has argued that quantum theories of consciousness suffer from the same fundamental weakness as classical theories. Neither can explain why a particular physical process, whether it is a neural firing pattern or a quantum gravitational collapse, should give rise to subjective experience. Replacing classical physics with quantum physics in your explanation of consciousness does not, by itself, bridge the explanatory gap. And yet, the theory endures. Not because it has been proven, but because the problem it addresses, the hard problem, the binding problem, the sheer astonishing strangeness of the fact that the universe contains experience at all, has not been solved by any other approach either. An orchestra, or whatever its flaws, is the only theory on the table that connects consciousness to fundamental physics in a specific, testable, quantitative way. If the theory were correct, and we must emphasize the conditional tense, it would reshape our understanding of reality in at least three profound ways. First, it would transform the debate about free will. In the classical picture of the brain, your choices are determined by the prior state of your neurons, which were determined by the prior state of your neurons before that, all the way back in an unbroken causal chain to the Big Bang. You feel as though you are making free choices. But in reality, every decision was fixed by physics long before you were born. This is the position known as hard determinism, and it is the default implication of any purely classical, computational model of the brain. Alternatively, if you introduce randomness, as some quantum interpretations do, your choices are not determined, but they are random, which is no better for free will. A coin flip is not a free choice. Orchestra or offers a third option. The moment of gravitational collapse is non-computable. It cannot be predicted by any algorithm, not even in principle. But it is also not random in the ordinary sense, because Penrose believes the outcome is influenced by non-computable mathematical truths embedded in the Planck scale geometry of spacetime. If this is true, and it is a very big if, then the orchestra or collapse is neither determined nor random. It is something new, something for which we may not even have the right word yet. It is the kind of thing that might conceivably ground genuine free will. A choice that is truly yours, not dictated by the past and not a product of chance. Second, the theory has radical implications for artificial intelligence. If consciousness requires quantum gravitational collapse in biological microtubules, then no digital computer, no matter how powerful, no matter how sophisticated its neural network architecture, will ever be conscious. A digital computer is, by definition, a Turing machine. It follows algorithms. It computes. And according to Penrose, consciousness is precisely the thing that cannot be computed. This does not mean that AI cannot be intelligent, useful, or even superintelligent in functional terms. It can pass tests, write essays, compose music, and generate strategies that no human could match. But it would do all of this without any inner experience, without any felt quality, without qualia. It would be, in philosophical terms, a zombie, the most accomplished and capable zombie in history. But a zombie nonetheless. The lights would be off inside. Whether this conclusion is correct depends entirely on whether orchestra or is correct. And we do not yet know that. But it is worth noting that as AI systems become more and more capable, the question of whether they are or ever could be conscious is becoming not merely philosophical but practical. If you're going to build machines that can suffer, you need to know whether they can suffer. An orchestra or provides, at the very least, a clear and testable framework for addressing the question. Third, and this is the vision that motivated this entire exploration, the theory reframes the relationship between consciousness and the cosmos. In the standard scientific worldview, consciousness is a latecomer. The universe existed for 13.8 billion years, expanding, cooling, forming galaxies, igniting stars, assembling planets, before any of it was experienced by anyone. Consciousness appeared only when evolution produced brains complex enough to generate it, and it exists only in the thin biological film on the surface of a handful of rocky worlds, as far as we know. It is an accident, a byproduct, an epiphenomenon, something the universe does in certain rare corners when the chemistry happens to be right. But if orchestra or is correct, consciousness is not an afterthought. It is woven into the fabric of reality at the deepest possible level. The same gravitational force that bends starlight around a black hole, the same curvature of spacetime that governs the orbit of planets and the collapse of dying stars, is the force that triggers each individual moment of your conscious experience. Your brain, in this picture, is not merely a biological machine that happens to think. It is a device that the universe has evolved to exploit a fundamental feature of its own physics. It is a gravitational antenna, tuned to the Planck scale, amplifying the whisper of spacetime collapse into the roar of lived experience. The same physics that operates at the center of a black hole, where spacetime curves to infinity, where singularities form, where the known laws of nature break down, operates at a gentler scale inside your skull, 40 times every second, weaving the stream of consciousness that you call your life. The universe spent 13.8 billion years doing nothing but expanding and complexifying. Stars were born and died, scattering heavy elements across the cosmos. Planets formed, oceans condensed, and on at least one world, molecules began to replicate. After billions more years of evolution, those replicating molecules assembled into organisms with nervous systems, and those nervous systems evolved neurons packed with microtubules, tiny quantum forests where spacetime could ripple and collapse. And through those forests, for the first time, the universe looked at itself. When you look up at the night sky and feel a sense of wonder, you are not merely a biological organism staring at points of light. You are the cosmos contemplating its own existence. You are the universe becoming aware of itself through a mechanism that is, if Penrose and Hameroff are right, as fundamental as gravity itself. Of course, there is no guarantee that they are right. Orchestra or remains a hypothesis, one of several competing theories of consciousness, and one that faces serious, unresolved objections. It could be overturned tomorrow by a single definitive experiment. That is the nature of science. Every theory is provisional. Every conclusion is subject to revision. And the only sin is to stop asking questions. But there is something that even the theory's fiercest critics must acknowledge. The question it asks, why does matter give rise to experience, is real. The question is not going away. And whatever the final answer turns out to be, it is likely to be at least as strange as what Penrose and Hameroff have proposed. The conventional tools of neuroscience have brought us extraordinary insights into the brain's architecture and function. But they have not cracked the hard problem. They have not explained why the firing of neurons feels like anything. They have not bridged the gap between the objective world of physics and the subjective world of experience. That gap is the deepest mystery in science. And it is possible, just possible, that bridging it will require us to look not outward at the stars but inward at the quantum geometry of our own minds. So let us return one last time to the question with which we began. You are reading these words right now. You are experiencing something, the meaning of the sentences, the visual pattern of the text. Perhaps a sense of curiosity or skepticism or wonder. Where is that experience? Is it in the electrical signals racing between your neurons? Is it in the synaptic connections that store your memories and shape your thoughts? Or is it deeper, in the quantum vibrations of tubulin molecules inside microscopic tubes? In the gravitational self-energy of superposed space-time geometries? In the moment when the fabric of reality itself chooses one shape over another? The answer is not yet known. The journey to find it is far from over. But what we can say with certainty is this. The 3 pounds of tissue inside your skull is not merely an organ. It is, by any measure, the most complex structure in the known universe. And it may be, if the boldest hypothesis in modern science is correct, the universe's way of knowing itself.